Hello! Welcome to the Armed Forces overview video for our hybrid prosthetic. Our customer is Professor Reva Johnson of Valparaiso University, who requested that we develop a hook-style prosthetic device for non-disabled users. Our hybrid prosthetic will be used to research the force required to actuate the hook open and close. This research will allow engineers, prosthetists, and patient care teams to better understand force requirements and muscle activity required to use a hook prosthetic. In addition to research, Professor Johnson also wants the prosthesis to serve as a demonstration tool for non-disabled users so that they may experience what it is like to use a body-powered prosthesis. Professor Johnson also requested that the design have a force amplification system to assist the user in opening the hook once a threshold force was applied.
Introducing the hybrid prosthesis. This design utilizes mechanical and electrical components to stimulate a real-life body-powered prosthesis, while collecting data on the forces a user may experience in its cable. This device operates as a standard prosthetic device until the force amplification switch is turned on, which allows the prosthetic device to assist the user in opening and closing the hook. The user may also collect the force data on an SD card by turning on the data recording switch. The data can then be saved by turning the switch off. Then the user may upload the data on a computer and access the files created on the SD card as a text file or Excel files.
The design consists of three major systems. The first is a body-powered data collection system. This system utilizes a figure 9 harness and a cable, allowing users to manually apply force to open and close the hook by extending or retracting their arm through the socket. The force applied to the cable is measured using a load cell, which sends this data through the amplifier. Here, the data translates the signals from the load cell into a format that the Arduino Nano can understand. The Arduino serves as the brain of the electrical system, interacting with every system on the device.
The second central system is the data recording system. When the data recording switch is in position, the Arduino communicates the data obtained from the load cell with an SD card adapter. The SD card adapter records the data onto an SD card, which can be inserted into the SD card to USB adapter to read the data on a computer. The final system is the force amplification system. When its switch is turned on, the Arduino controls a servo motor based on the data obtained from the load cell. Through this method, the servo assists the user in opening the hook when the user is applying a certain amount of force to open the hook, and it will close the hook when the user is applying minimal force. The force amplification and body-powered system operate on two separate cables to prevent a feedback loop occurring.
The 3D printed socket allows the device to be worn comfortably by the user. The socket consists of a flexible TPU sleeve insert with a rigid PETG platform. The TPU insert wraps around the arm of the user and is secured via adjustable Velcro straps. The rigid PETG platform consists of all the electrical components, fastens the hook in place, and provides extra security through the use of a handle. This socket allows for the device to be easily switched between users, which is conducive to use as a learning tool.
Overall, this design will serve as an important purpose in both conducting research for body-powered prosthesis and demonstrating how a body-powered prosthesis feels like to non-disabled users. It has been an honor to work with Professor Johnson and contribute to such an important research field. We hope you enjoyed learning about our hybrid prosthesis design. Thank you for listening.